everybody. Welcome back to Mathematical Statistics. We are going to GLERT today. GLERT stands for Generalized Likelihood Ratio Test, the acronym being GLRT. And this is an alternative to UMP testing, and both are an alternative to just common sense testing. Like, let's try this statistic. And I think if the null hypothesis is false and the alternate is true, it should be reflected in the statistic in this way. So we did the same thing with estimation. We started with sort of guessing and common sense. We moved to the UMVU, which was the greatest estimator in all the land, and that sort of corresponds to moving in hypothesis testing from just kind of using common sense to the uniformly most powerful test. And then we moved to the MLEs, the maximum likelihood estimators in estimation, and now we're moving to the GLERT, the generalized likelihood ratio test, which is sort of the same kind of move. So UMP tests often do not exist. They often do not exist in the two-tailed test case, although that's not a guarantee that it won't exist. And you're definitely going to have problems if you try to use really crazy spaces. I keep teasing that we're eventually going to see a hypothesis test where the null hypothesis is all the thetas for which some weird function of theta does some weird thing. So far, we've been doing very simplistic looking things. And even then, sometimes the UMP does not exist. But if it does exist, it may be intractable. It may be that you can't compute the probabilities you need to compute once you've simplified the likelihood ratio. So you should GLERT, generalized likelihood ratio test. Let's go. Our generic null hypothesis is that our parameter theta, which could be vector valued, is in some set capital theta naught, which is some subset of the parameter space, versus the alternate hypothesis that theta is in the rest of the parameter space. So that's the complement of this set I just wrote down, but with respect to the space, we write that as the full space theta, and then a backslash, which is like subtracting a set, the set from the null hypothesis, which again is the full parameter space intersected with the null hypothesis complement. So this is what we want to test. And the generalized likelihood ratio test is another recipe for giving you a statistic and a direction for your test. And that statistic is known as a generalized likelihood ratio, or GLR for short. We're going to use lambda just like we did before, and an x. Now, before we then had a theta naught and a theta 1, and those were values from the null and alternate hypotheses. But we don't have such things here. We've got this pretty generic setup. So we're going to define the GLER, if you will, to be, well, actually, before I define this, let's write down a likelihood. So I'm going to let L of theta be a likelihood for the problem. You've got x1 through xn, maybe IID, maybe not, from some distribution, and you can write down a likelihood. And I can write down a likelihood, and our likelihoods might differ a little bit by some constants. As long as you settle on one and you use that one for the whole problem, you're okay. So the likelihood will allow us to form a generalized likelihood ratio, which is defined to be the maximum of the likelihood, where theta is taken from the null hypothesis region, theta naught, divided by the maximum of the likelihood, where theta is taken from the entire parameter space. And we talked a little bit last time about why in my denominator I'm not maximizing over this region. It would be perfectly acceptable to do so. You can get a size alpha test, but doing it this way, we're going to have some nicer properties, which are going to be especially helpful for when the computations get bad. We're actually going to get asymptotic results here, so that if we can't find a distribution that we need in order to compute a probability and set it equal to alpha, we can say, well, if I have a large sample, I can get approximately this. So that's why we're maximizing over the whole parameter space and not the alternate part of the parameter space. But either way, this is like the maximum likelihood of seeing your data, period. And this is the maximum likelihood of seeing it when the null hypothesis is true. So if that's relatively small compared to the maximum over everything, then you would think that maybe the null hypothesis is not true and you would reject the null hypothesis. So this is what gives us the form of the test. The form of the GLERT of size or level of significance alpha is to reject a null hypothesis in favor of the alternative if this thing gets small. Now I'm going to put the capital letters into the GLER. And I'll say this needs to be less than or equal to K or C, just some constant, where, and I'm going to be lazy about writing this part, where K is determined in order to give a size alpha test. So that's it. That's a GLERT. Okay, so another way to write this GLER, this generalized likelihood ratio up here, is to say in the denominator, I have the likelihood at theta hat, where theta hat is the maximum likelihood estimator for theta for whatever this model is. And the numerator would be the likelihood evaluated at some theta naught hat, unlike theta naught, which throughout has been like a constant. This theta naught hat is an estimator or a random variable. And the theta naught hat is the so-called restricted MLE, or maximum likelihood estimator. And this means that we maximize the likelihood function over the region in theta where the null hypothesis is true. So let's start off with some examples to make sure we can find the restricted MLEs, and then we'll jump into some tests. For my first example, I'm going to take x1 through xn, IID, normal, mu, sigma squared, and I'm going to assume that sigma squared is known. We'll take that assumption away pretty quickly here. Suppose I want to find the GLERT. You know what? I don't want to go that far in this example. So let me just say I want to find the GLR, the generalized likelihood ratio, for the GLERT, for the actual test. For testing the hypotheses, my null hypothesis is going to be that mu is some fixed mu naught, and my alternate is going to be that mu does not equal mu naught. So I don't know if you remember, but in this case, we did not have a UMP test existing. We have, however, done this way back when with our common sense sort of thing, because the test involves the mean of the distribution mu. So we decided to look at the sample mean x bar. And because we want to reject the null hypothesis, if it appears that the true mean that is being sampled from is far away from mu naught in either direction, we decide to reject if x bar gets far away in either direction, where we defined what far away meant. So that was our common sense test. And now let's see what the GLERT gives us. So the likelihood is e to the minus 1 over 2 sigma squared times the sum as I goes from 1 to n of xi minus mu squared. That's just from the joint PDF. And I have dropped the constant in front, which usually looks like 2 pi sigma squared to the minus n over 2. But if you leave it, it'll be fine because you're forming a ratio and that part will disappear. So this is a likelihood. It is the likelihood I want to use here. Come on. What is going on? That's weird. Okay, so my eraser won't stick. Okay, so I don't even want to do the whole GLERT right now. I just want to do the GLR. So let's define it. It is this lambda thing. And to find it, we need the MLE for mu, which we denote by mu hat. And we know what this is. This is x bar. If you don't, you can go find it. You could take the log of this and take a derivative and set it equal to 0, and you'll find that it's x bar. Now, I want to find the restricted MLE for mu. We're going to call this mu naught hat. And now we want to look at the likelihood function. And I'm going to draw a generic thing. It is not the actual graph of what I just circled. I'm going to put mu here and the likelihood function here. And in fact, for the normal distribution, mu can be negative. So I'm making it look like it has to be positive, but this is going to extend in both directions. And so suppose our likelihood, I don't know, looks like this. The MLE is where it is maximized. So this is where X bar is going to be on this graph. And that will change if the data changes, because even though we suppress the notation, the likelihood does depend on the data. So the next time you take a sample of data, that hump will kind of move around and maybe in some cases completely change the shape of things. Now let's look at the region where the null hypothesis is true. The null hypothesis consists of a single point. In general, if you have some region where the null hypothesis is true, you're going to want to maximize the likelihood over that region. We have a region, but it is a single point. I don't know where it is. It could be here, it could be here. It's not going to be here because the probability that X bar is going to land on that mu naught is 0 because X bar is a continuous random variable. So it's somewhere and it's fixed, and X bar will not land on it with any positive probability. But let me get rid of some of these dots. Okay, so suppose it is here where I have this green dot. I want to maximize this function over all those values. There's only one value, and here's what its function is at that value. This is L of mu naught, and this is mu naught. And if you're looking at just that region consisting of one point, that is the place where the likelihood over that region is maximized and minimized, and its average value, it's everything. There's only one point there. So the restricted MLE maximizing over the single point is just going to be the argument that maximizes things. It's going to be that single point. We got an MLE and a restricted MLE, and the generalized likelihood ratio. I could put a capital X here or lowercase x. If we were actually doing the test, I would probably put a lowercase x vector because I would just be doing algebra, but then make things capital at the end when we're computing probabilities. Whatever you want to do. But this is L of mu naught over L of X bar. I guess I'm making them look lowercase right now. And the L function is still right here. It's circled. And you can divide or maybe write this like this. The sum of the xi minus mu naught squared minus the sum of xi minus x bar squared. And that is the generalized likelihood ratio. So we will finish this test eventually, but right now I just want to do some more examples of the restricted MLE. But if we were to continue on the test here, we would set this less than or equal to some constant k and try to start simplifying the left-hand side so that we've isolated the x's. And again, we will do that today. Let's look at another example of just finding the generalized likelihood ratio. I want to look again at a normal distribution, x1 through xn, IID, normal, mu, sigma squared. And now I want to assume both of these parameters are unknown. So I'm going to start with what might be kind of a weird hypothesis. It's just so specific, but let's find the generalized likelihood ratio for testing the null hypothesis that mu is equal to a particular value mu naught, and usually we would just write a comma there, sigma squared is equal to a particular given value. The alternate hypothesis, I'm just going to write not HO, because I have a few cases to consider, like if the mu went wrong or the sigma squared went wrong or they both went wrong. So it's easiest just to write not HO. The likelihood is a function of mu and sigma squared, and I can no longer drop the sigma squared to the minus n over 2 in the front. And in fact, if you want to leave the 2 pi in there as well, you're going to be just fine because it's going to go away in the ratio. So this is what I'm choosing to be a likelihood. You can't drop the sigma squared because that is not constant in this problem. And the unrestricted MLEs, we already know these. We've seen them a few times. They are mu hat equals x bar, and sigma squared hat equals not our version of sample variance, but the biased version of sample variance, the sum xi minus x bar squared over n. Or if you'd like, this is n minus 1 over n times our version of the sample variance. But you might see some people just writing this because some people do define their sample variance this way, which is a little bit biased. I don't think it's worth putting that in there, so let's just, what is going on? My eraser just keeps timing out or something. Sorry about that. Okay, so let's now look at the restricted MLEs. Now, if you were to graph the likelihood, then it's going to be over, like it's going to be a three-dimensional sort of drawing where on the plane, on the ground, you have the mu and sigma squared axis, and then you have a likelihood over it. And we want to maximize that over the region in the mu sigma squared plane where the null hypothesis is true. But just like in the previous problem, we are looking at one point in this two-dimensional space, and the maximum is going to have to occur at that one point, as well as the minimum and the average and really anything else you want to compute with the likelihood. So my mu naught hat, my restricted mean, is going to be mu naught, and my sigma naught squared hat is going to be sigma naught squared. And then the generalized likelihood ratio is the likelihood with the mu naught and the sigma naught squared plugged in over the likelihood with the, so I've got this looking lowercase, so I'm going to say lowercase x bar, and let me just write this as sigma squared hat, even though I didn't use a hat anywhere else. I don't want to plug that whole thing in. And I'm not going to write this out. I think we're eventually going to do this example as well, but here's your function. So you can start forming that ratio, which is quite ugly, even for a simple normal distribution problem. We're going to get lots of practice simplifying those. Let's move on to the third example of finding the GLUR. Once again, we're going to look at the normal distribution, and it's going to be just like the previous example where both parameters are assumed to be unknown. What I'm going to do is change up the hypotheses for this problem. I'm going to say that mu is some mu naught versus the alternate hypothesis that mu does not equal mu naught. So here's the thing. Both parameters are unknown, including the sigma squared, but the sigma squared is not involved in the hypotheses. So what do? You still have the idea of the MLEs, the unrestricted MLEs would be mu hat equals x bar, and sigma squared hat equals the sum of the xi minus x bar squared over n, the biased version of sample variance. The restricted MLEs is where the work is. So what is our estimator for mu when we're restricting ourselves to the space where mu equals mu naught? Our estimator for mu is just mu naught. To find sigma naught squared hat, we need to maximize the likelihood under this restriction. And I'm pretty sure most of you can guess what this is going to be, but let's just look at it. Let's try it just to make sure. So this is going to be assuming mu equals mu naught, so there's only one unknown. This is sigma squared to the minus n over 2 e to the minus 1 over 2 sigma squared, sum of the xi minus mu naught squared. So Maximizing it, I'm going to take the log. I'm going to look at the log likelihood. I'm going to get minus n over 2 log of sigma squared plus the log of the e, which is going to be minus 1 over 2 sigma squared, sum of the xi minus mu naught squared. We're going to set this equal to 0 and solve for sigma squared. You can do whatever you want. What I like to do is, well, I haven't taken a derivative yet, so I think we should do that. Okay, so I'm going to take the derivative with respect to sigma squared. I get minus n over 2. The log of, say, x, the derivative is 1 over x. In general, the log of a function of x is the derivative of that function over the function itself. Here, we're not talking about x, we're talking about sigma squared. So the log of sigma squared, if you take its derivative with respect to sigma squared, you get the derivative of sigma squared with respect to sigma squared, which is just a 1, over the sigma squared itself. For the other fraction, it's like having sigma squared to the negative 1, and when you take the derivative, you'll get negative sigma squared to the negative 2, and that'll combine with this other negative sitting here, and ultimately you'll get positive 1 over 2 sigma squared squared. Set equal to 0. This should not be set equal to 0 because we are not looking at the derivative up here. So usually when I have the eraser, I have to, make a motion to get the pen back. But now after I lift the eraser from my screen, it's going back to the pen. So sorry about that. I didn't notice that before we started class. Okay, so to solve this, I am going to take the larger denominator and multiply both sides by that. On the right side, we'll still get 0. On the left side, we'll get minus n sigma squared plus the sum of the xi minus mu naught squared. And finally, you solve for sigma squared and you throw a hat on it. And you make things capital. Now, if you're just doing this as a standalone MLE problem, you would write sigma squared hat. But because this is going to be my restricted MLE, I'm going to go ahead and write sigma naught squared hat. It's going to be the sum as I goes from 1 to n of the capital Xi minus mu naught squared over n. And so the unrestricted MLE had an X bar here, and now we're restricting ourselves to when the mean is known and fixed at mu naught. So I think a lot of you probably guessed the restricted MLE for sigma squared, but this is what you would have to do to show it. All right. Okay. So quick recap. We have the unrestricted MLEs. We have the restricted MLEs. We have the likelihood. I actually never wrote down the full likelihood. I wrote it down only when I restricted mu. So the full likelihood L of mu and sigma squared, it's going to be sigma squared to the minus n over 2 e to the minus 1 over 2 sigma squared, sum of the xi minus mu squared. And then finally, the generalized likelihood ratio, we call this lambda of x. This is the likelihood at mu naught and our sigma naught squared that we've just written down over the likelihood at mu hat sigma squared hat, which is going to be a ratio of e's, which is going to be e to a difference. And I don't think we're going to end up doing all these examples in the remaining time, but we're going to do at least one of these long computation examples, hopefully today. You would set this less than or equal to k and solve for k using the definition of alpha. Before moving on to finding an actual GLERT to actually doing the test, I want to do one more example. So far, we have had all simple null hypotheses. Suppose we have x1 through xn, IID, normal, mu, sigma squared. And because this is going to get complicated enough as it is, I'm going to assume that sigma squared is known. So there's only one unknown parameter here. And I want to find the GLR, the generalized likelihood ratio, for testing the null hypothesis that mu is less than or equal to some fixed mu naught versus the alternative that mu is greater than mu naught. So now the thing that's changed is the null hypothesis has this inequality. So we're actually going to have to maximize the likelihood over a non-trivial region. The likelihood here is L of mu. I'm leaving off the sigma squared because it's constant in this problem. And we can define this to be e to the minus 1 over 2 sigma squared sum of the xi minus mu squared. So we're going to need the MLE, the regular old unrestricted MLE, and we know that that is the sample mean x bar. So here's where it gets a little bit tricky. The restricted MLE, mu 0 hat. I want to find this. So we do have a fixed value, but that's not the whole null hypothesis region. The null hypothesis region is all the mu's less than or equal to that value. Let me draw a sort of generic likelihood. Suppose this is the mu axis and L of mu. And in this picture, this is going to be where x bar is because that is what maximizes this likelihood. The mu naught is fixed somewhere. Let's say it's just a number, and let's say it is here. Now, you know what? Let me do this one first. Let's say it is here. Mu naught is here. In this problem, where the null hypothesis is all mu less than or equal to mu naught, this is the null hypothesis is true region. So mu naught hat is the maximum or the maximizer, the argument where it's maximized over the null hypothesis region. In this picture, the overall maximum of the likelihood happens to fall in this null hypothesis region. And that means that the maximizer is x bar, but this is if mu naught is greater than x bar, or greater than or equal to would be okay. Now, mu naught, given in your hypotheses, is a fixed number, but every time you grab a random sample, your likelihood shifts around. And for the next sample, it might look like this. So this is another L of mu for a different sample. In this case, since it's maximized at x bar is going to be over here. And so I am going to, let me continue what I was writing at the bottom by putting some brackets in. I'm going to talk about the case if x bar is greater than or equal to mu naught, or you can put the equal sign on either part of this piecewise function. So looking at the pink graph only, here is where the maximum occurs, but the restricted MLE is going to maximize it over this region. So our likelihood only has a single maximum, as do most likelihoods. When you find the MLE and you take your derivatives and stuff, you only find usually one critical value. And that means that over this region, the maximum is going to occur at an endpoint, namely right here. This is the largest part of this curve over this restricted region. That means that the restricted MLE occurs right at mu naught. And that is the rest of the answer down here. We're going to get mu naught if we're down in that region. To finish off the GLUR, the generalized likelihood ratio, this is going to equal, well, it's the likelihood at mu naught hat over the likelihood at mu hat. If mu naught is greater than x bar, then mu naught hat is x bar, which was mu hat. So we're going to get L of mu hat over L of mu hat, or 1, if mu naught is greater than X bar. In the other case, the maximum likelihood estimator for mu over the restricted region, this is going to just be L of the constant mu naught over L of X bar. One more time, it doesn't matter where you actually end up putting that inequality. But here is the generalized likelihood ratio, which we would then set less than or equal to k and solve for k using alpha. And this looks a little more complicated. I will definitely get you started on this today, but probably not finish it all because it's just tedious and messy, but I'll show you how to get started on it. Before that, let's do a GLERT. Let's actually do a hypothesis test. Let's find some GLERTs. For my first example, I'm going to stick with the normal distribution, x1 through xn, IID normal, mu sigma squared with sigma squared known. And I want to do the first example we talked about in our GLRs today, that mu is mu naught versus the alternative that mu does not equal mu naught. In this case, we saw that no UMP test exists. So given what we know in this course right now, our alternatives are to try to do a common sense test or to GLERT. And since we're in the GLERT section, let's GLERT. Okay, so we really have done the first half of the work already. We have a likelihood as a function of mu. It is E minus 1 over 2 sigma squared, the sum xi minus mu squared. We have our regular MLE, mu hat equals x bar, and we have a restricted MLE, which maximizes the likelihood when the null hypothesis is true, but there's only a single point there. So the argument that's going to maximize that function over the region that is just a single point is that point. The generalized likelihood ratio, I'm going to keep things lowercase. You can make things capital. This is just my algebra step. This is the likelihood at the restricted, oh, by the way, this should have a naught on the subscript. And so we should have the restricted MLE over the unrestricted MLE. This is this E function with mu naught plugged in, divided by that E function with X bar plugged in. So I'm going to go ahead and subtract already. This is going to be E to the minus 1 over 2 sigma squared, the sum of xi minus mu naught squared minus the sum of xi minus x bar squared. That is the generalized likelihood ratio to do this test. I'm going to set this less than or equal to some constant k, or whatever your favorite constant is. And I want to do as we've always done. I want to try to isolate the x stuff on the left-hand side. If you were to square these out, I can see right away that we're going to get at least some cancellation of the sum of the x's squared. Let me multiply that out. I have E to the minus 1 over 2 sigma squared, the sum of the xi squared minus 2 mu naught sum of the xi plus n mu naught squared, and then I need more brackets, minus the sum of xi squared minus 2x bar sum of the xi plus nx bar squared. And we're going to, well, I'll write it. We'll set this less than or equal to k. This cancels with this. And some other things here we can combine. Let's do it. I think to make this easier to combine, I would like to get, I've got two statistics in this expression. I've got some x bars and the sums of the x's. And I have x bar squared, but you can think of that as a function of x bar. I don't want two statistics if I can help it. So I am going to or not define, I'm going to rewrite the sum of the x's as n x bar. I'm going to put everything in terms of x bar. If you want, you could put everything in terms of the sum of the x's. So this over here is also going to be n x bar. And so this is e the minus 1 over 2 sigma squared minus 2n mu naught x bar plus n mu naught squared plus 2 x bar 2n x bar squared minus n x bar squared less than or equal to k. This guy doesn't have any x's in it, so you don't have to write this out if you see what you're doing, but you could break this up into the product n mu naught squared and then the rest of it. And this is just going to be a constant that can go to the other side. Before doing that, let's figure out what the rest of this is. I have 2n x bar squared minus n x bar squared, so that leaves me with a single n x bar squared. And then I have this term minus 2n mu naught x bar less than or equal to k. Divide this to the other side. Whether that exponent is definitely negative, but regardless, e to a power is never negative. So when we divide, we're dividing by something positive, and the direction of the inequality will be maintained. And we'll have some new constant here that I'll call k1, where k1 is k divided by that circled thing. It still looks a little tough because our stuff that's going to be run, and when we capitalize things, is in two places, in two statistics. But what if we combine them by completing the square? If you recall, for completing the square, oh, and I lost this. So let me fix that. Okay, that looks much better. I'm going to pull out the lead coefficient, the n, and I've got x bar squared minus 2 mu naught x bar less than or equal to k1. So if you do completing the square formally, you may recall that you're going to take the lead coefficient of the degree 1 term, divide that by 2, square it, and add that in. I am just going, and you can do that, by all means do that. But this appears to be something squared if I had a final term over here. I'm just going to sort of do it like, I don't know, without formality. This appears to be x bar minus mu naught squared. But if you were to square that out, you get x bar squared minus 2 mu naught x bar plus mu naught squared. So I need to subtract a mu naught squared so that this line is equal to the line above, less than or equal to k1. Get there however you want to get there, by completing the square more formally, or thinking about what this might be if it was something squared and how you would need to adjust it. We can break this up into two e parts, exp over 2 sigma squared less than or equal to k1. And there's no unknown mu's here, so that can be divided to the other side, giving us a k2. Then we'll get all of this less than or equal to k2. And then I'm going to take the log on both sides. So we'll get minus n over 2 sigma squared x bar minus mu naught squared less than or equal to a constant k3, which is, in my case, the log of k2. Then I'm going to divide by this, which is negative, so that will flip the inequality. I'll get x bar minus mu naught squared greater than or equal to some k4. Okay, so we could, at this point, find k4 and give the recipe to the person that wants to do the test like this. I have a couple of options there, and I kind of think I don't want to find K4. I'd like to give them the test in a different form. So here is one option, or option one. I am going to take the square root of both sides of this thing and get x bar minus mu naught greater than or equal to the square root of K4, and or x bar minus mu naught is less than or equal to the negative square root of K4. If I move the mu naughts over, we get mu naught plus the square root of K4, or mu naught minus the square root of K4. I kind of want to call this K5, but these two numbers I just under squiggled are not the same thing. So if you want to call them K5 and K6, go ahead, but I think I'd rather only have one unknown. So let's leave it in this form and say that the form of the test is going to be to reject the null hypothesis in favor of the alternative. Not necessary to say in this case where our parameters take up the whole space, but I just like the sense of completeness. If either capital X bar, the sample mean, is greater than or equal to mu naught plus the square root of K4, or it is less than or equal to mu naught minus the square root of K4. And this form feels good, right? We want to test whether the true mean is mu naught or not. So we want to reject the null hypothesis if we're up above that mu naught or down below significantly that mu naught. So I feel good about this. I hope you do too. And to find the K4, we're going to use alpha. Alpha is the maximum over all the mu's in the null hypothesis, which is just a single mu. The probability we reject the null hypothesis when the parameter is mu, maximizing over a single mu just means plugging it in. So I'll get a mu naught here. And then this is going to be the probability that x bar is greater than or equal to mu naught plus the square root of K4. You know, I can make this a new constant. Let's call this square root K5. So let's say mu naught plus K5, mu naught minus K5. But again, I can't make this whole thing into a constant without introducing a second constant. So back down here, I'm going to say plus K5, or x bar is less than or equal to mu naught minus K5 when the parameter is mu naught. These are disjoint events. They can't happen at the same time. So by disjointness, we get the sum of these individual probabilities, and they're both under the assumption that the parameter is mu naught. And now I've got the mean of the distribution, and that's telling me that this x bar has a normal distribution with mean mu naught and variance sigma squared over n, which is known to us. So let's standardize these. This is the probability that x bar minus mu naught over sigma over the square root of n. I'm going to do the same thing to both sides. So I get mu naught plus K5 minus mu naught over sigma over the square root of n when the parameter is mu naught. And something similar over here. I'm rushing now to make up some of that lost time. Under the assumption that the true parameter is mu naught, this is a standard normal and can be called z. And at that point, and this is going to simplify a little bit into the square root of n K5 over sigma. And I no longer need the mu naught because the distribution of z is a normal 0, 1 and doesn't depend on mu naught, plus the probability that z is less than or equal to the negative square root of n K5 over sigma. Okay, this whole thing is supposed to be alpha, and we're down to a standard normal and a number and the negative of the number. So the standard normal distribution centered right here at 0, I've got a number and the negative of the number. So everything, because we kept only one K5, is nice and symmetric. So this means that I want to be above a number with probability alpha over 2. And below the same version of that number with probability alpha over 2. So if I want alpha over 2 up here, this is going to be called z sub alpha over 2. This is the negative of z sub alpha over 2. In either case, if you look at this square root of n, k5 over sigma, you get that k5 is sigma over the square root of n z sub alpha over 2. So returning to these tests, those numbers are going to go right here. And the final test, the GLERT of size alpha for the null hypothesis that mu equals mu naught versus the alternative that mu does not equal mu naught, is to reject the null hypothesis in favor of the alternate hypothesis if x bar is greater than or equal to mu naught plus sigma over the square root of n z alpha over 2, or x bar is less than or equal to mu naught minus sigma over the square root of n z alpha over 2. That is the GLERT. And we are done with option 1. So we had a generalized likelihood ratio. We set it less than or equal to k, and we solved it down to a certain point and wanted to solve for the k. And that's where I said we had an option 1. Another option, by the way, this is the expected test. This is the test you see in data-oriented stats courses. This is how you do a two-tailed test for the mean of a normal distribution. So nothing surprising here. But let's talk about a second option for finishing off this test. And what I mean is starting from this, I want to do something just a little bit differently. So x bar minus mu naught squared greater than or equal to k4. I already forgot what that was. Yeah. So let's suppose we're there. What I did was take the square root and try to isolate the x bar. But we then had to sort of unisolate the x bar when standardizing it. So maybe we should not simplify this, but build it up. Maybe we should say that, let me get a color, we could put this over sigma over the square root of n, and this over sigma over the square root of n. And then on the left side, I have, I'm going to go capital, this guy squared greater than or equal to, I probably going to call this k5. I'm debating now whether or not I want to go back to this as my rejection rule and report the k4, but I don't think I will. So yeah, I'll call it a new constant. Okay, so I'm not writing out all the probability statements, but under the null hypothesis, that is under the assumption that it's true, the x bar is normal with mean mu naught and variance sigma squared over n. So that means that this thing inside is normal 0, 1. And when you square a normal 0, 1, you get a chi-squared. So this entire thing has a chi-squared 1 distribution under the null hypothesis, i.e. when the null hypothesis is true. So I want to solve alpha equals the probability that W is greater than or equal to k5, where W is a chi-squared random variable with 1 degree of freedom. And this means that the critical value k5 in our notation is chi-squared sub alpha, comma 1, because that's the number that's cutting off area alpha in the right tail. Okay, so the final test is that the GLERT of size alpha for the null hypothesis that mu equals mu naught versus the alternate hypothesis that mu does not equal mu naught is to reject the null hypothesis in favor of the alternate hypothesis if x bar minus mu naught over sigma over the square root of n squared is greater than or equal to this chi-squared critical value. So here's another way to represent the test. It's not a different test. If you were to solve this by taking the square root on both sides, you're going to have a test that looks like our other test, but in terms of a chi-squared critical value. You're going to get x bar greater than or equal to mu naught plus the square root of a chi-squared alpha 1 critical value times sigma over the square root of n, or x bar less than or equal to mu naught minus the square root of this chi-squared critical value, sigma over the square root of n. And if you go to a chi-squared table or software, and you say for a chi-squared distribution with 1 degree of freedom, what number is going to cut off area alpha to the right? This is actually going to turn out to equal z alpha over 2. This is going to turn out to equal z alpha over 2, the negative being outside that circle. That's not obvious, but check it out if you have some spare time. Just fix an alpha and look up some critical values. You're getting the same test. So we're done with our first example of a full GLERT. Okay, the final thing for today is I just wanted to get us started with an example. I really only wanted to get us started with this, even if we weren't running out of time, but I can act like it's because we're running out of time. This example was where we had a composite null hypothesis. So we had IID, normal, mu, sigma squared, and sigma squared known. So we were looking at the test. The null hypothesis was that mu is less than or equal to mu naught versus the alternate hypothesis, mu is greater than mu naught. And this was the case where we got a weird generalized likelihood ratio that was defined in a piecewise way. Our lambda of x was e to the negative 1 over 2 sigma squared, negative 2 mu naught n x bar plus n mu naught squared plus n x bar squared. And this was if mu naught was less than x bar and it was 1, if mu naught is greater than or equal to x bar, or the equal sign could be in either position. I don't know if I actually simplified it to this, so you might still have it as a sum of something squared minus a sum of something squared. I can't recall. Okay, so I just want to get you started on finding alpha. We want to reject the null hypothesis in favor of the alternative if lambda of capital X is less than or equal to k, or some k to be determined to give a size alpha test. To determine k, we're going to have to use the equation alpha is the maximum over all mu's less than or equal to mu naught. That's the null hypothesis. The probability lambda of x is less than or equal to k when the parameter is mu. So ignoring this, I just want to get you started on how you might compute this, and then you could maximize it over that region. If you have the probability that lambda of x is less than or equal to k when the parameter is mu, so I am not dropping that maximum. I am just sort of ignoring for the moment. I want to tell you how to compute a probability for something that's defined piecewise like this. The value of this depends on where the x bar is. So you could condition on where x bar is, and it would look like this. You could say x bar, so I'm not under the null hypothesis assumption yet, because I'm just trying to work this out, and then I'll go back and look at all the values for the null hypothesis being true. But x bar is either greater than or equal, or I'm sorry, greater than mu naught or less than or equal to mu naught. So I could write this as the integral from minus infinity to infinity of the probability that lambda of x, and this is still capital, is less than or equal to k when the parameter is mu. I'm going to denote that over here because I want space for this conditional statement that x bar equals some value. You can call it little x bar. I'm just going to call it little x, one-dimensional thing, times the PDF for x bar at little x. So we're just talking about a generic parameter mu, and this is going to be the normal mu sigma squared over n PDF. We're then going to use the fact that x bar equals x to plug that in, and we're going to break up this integral into minus infinity up to mu naught plus a mu naught to infinity. And now I really am out of time, so I may pick up on that next time. If not, I promise I'll write it up. But that's the idea. If you have a piecewise defined GLR, then when you come down to computing a probability like this, you say, I could make this a little easier if I knew which region I was in, so you can condition on that region. So actually, I think we should pick that up. We're going to pick that up next time. And then we're going to do a GLERT for a non-normal distribution. And then I'm going to give you the real reason GLERTs are great, because these computations are ugly and we're just doing nice normal distributions. The idea is that under certain assumptions, if you look at the generalized likelihood ratio, under certain assumptions, if you take -2 times the log of it, this is going to converge in distribution to a certain chi-squared distribution. We're going to prove this next time. And so if you can't do the probability calculations for an exact GLERT, you could use this fact to come up with an approximate large sample GLERT using chi-squared critical values, even though those might not be the appropriate critical values for the particular problem. So it's like a central limit theorem kind of thing. We're going to get a distribution for not exactly the GLR, but this function of it. And we're going to work with that to find our cutoff next time on mathematical statistics.